Sure. Thank you to the organizers for inviting me. It's a pleasure to be here. I'm sorry I missed all the talks yesterday, but thank you for coming. Okay, so, so I'd like to talk about some things that I've been thinking about recently. So, this is a conference about piecewise linear homeomorphisms of manifolds, so I'll try to involve that somehow. So, so M, so this will be a manifold. So usually one should put some restrictions on it. I'll assume that it's just going to be closed and connected always.
Could you write a little bigger?
Yeah, sure. Right, which should always be closed and connected to make things a little bit simpler. And a lot of the time I'll want to impose some structure on it. So at the very least, it should be triangulable, but maybe smooth. Or PL. Okay, so one thing that also connects to Yash's talk which he just gave was sort of the sense in which a group of homeomorphisms of M can recover the underlying topology of M, or M up to homeomorphism. Okay, so so many groups of homeomorphisms of M recover M up to homeomorphism. So maybe I should say homeomorphism groups. All right, so let me say a little bit more precisely what I mean by that. Okay, so in the context of maybe PL manifolds, then we have this group of piecewise linear homeomorphisms of M. Okay, and so then this sits inside of this much larger group of homeomorphisms of M. Okay, and so then what Yasha's favorite theorem that he alluded to in his previous talk is this thing, Rubin's theorem, which basically tells you that the isomorphism type of PL of M acting as a group of homeomorphisms, it's not just PL of M, but many sufficiently complicated subgroups of homeo of M, they are enough to recover M for you as a topological space, okay, up to homeomorphism. So for me, an isomorphism type of groups is a little bit too much information. Okay, so what I like to think about are maybe facts that are true inside of a group. So maybe first order group theoretic statements or something like that that are true within a group and the degree to which they determine the underlying manifold. Okay, so in some very general sense, I'm not going to bother giving all the underlying background and even really very precise statements here. I'll just say that that there are group theoretic sentences in, say, PL of M, which determine M up to homeomorphism. So maybe slightly more precisely, so what do I mean by a group theoretic sentence? So that's just going to be some sort of string of of symbols, for all elements there exists some other element, such that for all there exists some combination of such things, and then some formula without any quantifiers. Okay, and so then if that's true in PL homeomorphisms of some other manifold, okay, so there's such a sentence that it's true in PL of M, so that if that sentence is also true in PL of N for some other manifold, then M and N have to be homeomorphic to each other. Okay, but now, great. Such a sentence is usually going to be extremely complicated. And so the basic reason maybe that such sentences even exist is because these groups like homeomorphism groups of manifolds are somehow they're sort of self-aware, and that's both sort of interesting and also kind of bad. So what do I mean precisely by self-aware? So take something like the homeomorphism group of M. So it's just a group, right? You can multiply group elements inside of it, and you can talk about things like, okay, the product of these two elements is equal to this, or it's not equal to that. Okay. But it turns out that the group theoretic language is so powerful that it can model essentially anything that you can talk about in set theory. Okay. So in particular, this homeomorphism group can talk about itself in the abstract. It can build an internal model of itself, and it can, among sort of all the possible homeomorphism groups of manifolds, it can pick out which one is the one that it is isomorphic to. Okay. And so that's somehow very, very complicated, and you can imagine that, okay, if the group theory can say something like that, then it can probably say more than is somehow manageable intellectually. Like, how can you even understand such a thing? Well, you cannot really. You can't determine if a particular group theoretic sentence is going to be true inside of a homeomorphism group because of, it's worse than like Gödel indecidability. It's worse than you can't, prove that some statement is true. I mean, so the truth of many statements in homeomorphism groups of manifolds are independent of the axioms of set theory. So that's some sense in which this is bad. Okay. So what I'd like to talk about today, more than just sort of illustrating how badly behaved these sentences can be, is to try and understand what is sort of the simplest way or the least upper bound on this problem of recovering the manifold from a homeomorphism group or from some sort of data encoding the manifold itself. Okay. So
does that mean, if we're going to do logic like that, does that mean if you take one of these AI things, you can have a map of all the manifolds, PL manifolds that exist built into it? Because it would just be a sequence of logical statements, one for each manifold.
Sure, yes, but the sort of entangling so disentangling the signal from the noise would be basically impossible. Well, in some precise sense, no reasonable computational model would be able to do that. So there'd just be a lot of sort of garbage and a lot of, well, so yes, all the sort of data that would be useful possibly to recover a piecewise linear manifold would be somehow listed. That's true. But then to actually practically implement some sort of recovery is impossible with any sort of reasonable computational tool. But what I'd like to talk about is maybe something that is more reasonable, given how difficult this is already. Perfect. Great. So this self-awareness for homeomorphism groups, full homeomorphism groups of manifolds, essentially arises from the fact that the homeomorphism group of a manifold knows what's called second-order arithmetic, which is basically says, okay, it knows how to do arithmetic on the natural numbers, but it also knows what all the subsets of the natural numbers are. So it can do basically anything that you do as a mathematician in your everyday life. Okay, so for piecewise linear manifolds, usually you don't get that much information. This group is much more restricted, but at least it will know at least as much as full arithmetic. So there's a precise statement that I can at least state. This is a theorem due to Clément Lasserre, which says that Thompson's group F is bi-interpretable with arithmetic, which is to say the natural numbers with addition and multiplication and the order. So what this means, this has a precise meaning in model theory. For this talk, it suffices to say that, okay, this is the natural numbers together with everything that you do in arithmetic, and it is enough to recover Thompson's group F. Okay? And on the other hand, F itself is complicated enough to recover this structure. Okay? And so they're sort of equally complicated. Okay. And returning to this sort of self-awareness of homeomorphism groups, so Thompson's group does have some sort of self-awareness in the sense that whenever it acts on some manifold in a way that's sufficiently complicated, then that manifold has to be the real line. So when I say, I'm eliding a lot of sort of dynamical details there, but there's some sort of self-awareness that's inherited by F. Okay, and so, okay, so then, how complicated is this structure, okay? And what does it have to do with sort of these group theoretic sentences which are enough to recover how complicated these underlying piecewise linear manifolds are? Okay, so okay, so maybe then to switch gears a little bit and to approach the sort of something more tractable, we can ask something more basic, like, okay, so consider manifolds encoded as finite simplicial complexes. Okay, so if I'm saying that, that manifolds should at least always be triangulable, then this is something that makes sense. Okay, and so then a finite simplicial complex then is just telling you, okay, you have some set of vertices, then you have some edge relation, and you have some relation that tells you when k vertices span a k-1 simplex, and so on. Okay, so then, a basic question then is, if I give you two such things, m and n, when are m and n homeomorphic? So this sounds like a different question from everything that we've talked about so far, but it really isn't, right? Because if you are given a finite simplicial complex, then you can write down lots and lots of homeomorphisms on it. You can even have a computer compute a lot of sort of rational homeomorphisms of it, some that will be so complicated enough that they will be forced by this machinery that I sort of outlined here to determine what the underlying manifold is up to homeomorphism. Okay, so then how do we sort of extract sort of this, the most basic question of if I give you two finite triangulations of manifolds, how complicated is the homeomorphism relation between them? Okay. So that is what I'd like to talk about for the rest of the talk. So one of the reasons I got interested in this question is because there was this paper by Harrison, Traynor, and Melnikov, which it explicitly asks this question, like if I give you two manifolds, maybe compact manifolds, how difficult is it to determine whether or not they're homeomorphic to each other? And so the thing is that they never really told the reader what it means to be given two manifolds. So one way to understand that is that you're given a finite simplicial complex, which is supposed to be a manifold. Another way that you could imagine it is this is given to you as some subset of a Euclidean space, but it should be sort of tractable in the sense of computation. So what that would mean is that you have some Turing machine which tells you some dense subset up to arbitrarily high precision if you run it for long enough. And so that determines for you some closed subset of a Euclidean space. And then there are all sorts of questions there, like how do you tell if it's a manifold first? And then how do you tell if two of them are homeomorphic to each other? So that second point of view is too difficult for me. So I'm just going to stick with finite simplicial complexes. Okay, so right, so the finite simplicial complex then can really, so I said we can encode them as natural numbers. Okay, so what do I mean by that? Well, you can imagine that the data of assembling a finite simplicial complex is just some string of natural numbers, and that can just be simply encoded as a single natural number. And so then there are simplicial complexes, maybe simp-comp, which are some subset of n, okay, and then there inside of here there are things that are manifolds, okay, and then you have homeo of manifolds, which naturally sits inside of n cross n, is some relation, okay, and so how complicated is this subset is really what this question is asking. So when you say how complicated it is, well, so hopefully it is cut out by some formula that you can write down in arithmetic. So there should be some string of quantifiers which quantify over actual natural numbers, and then some formula that has no quantifiers in it. And this is some generalization of an affine variety, except in arithmetic. So you might have more quantifiers. Okay, great. So so then to talk about how complicated these sets are in some precise way, one has to sort of look into computability theory, okay, and something called Turing jumps. Okay, so if you're returning to the original question, you want to know, are two triangulated manifolds actually homeomorphic to each other? Then the best possible thing that you could hope for is that you could just feed these codes to a Turing machine, and then it just says yes or no. Okay, so that's not possible, and I'll explain that in more detail in just a second. Okay, but then you can. There's more than just Turing machines. So Turing machines can have access to oracles, which are more complicated subsets of the natural numbers, which are usually not themselves computable, and then their computational power increases. Right, so in computability theory, so if you, again, I'll just write sort of this block 0 for the computable functions. So this is, you imagine this is every possible function that can be computed by a Turing machine with no input. So it's just everything that you can compute with just the empty set as your oracle. Okay. So if you've studied any computability theory, you may know that there is something called the halting set. Okay, so the halting set says, okay, I give you a computable function, and then I give you an input. Will this computation converge on that particular input? Okay. So that itself can be thought of as a subset of the natural numbers. Okay, and it itself is not computable. Its characteristic function is not computable. So that's oftentimes written as 0 prime. This is the halting set. So what this is really asking is you have some sort of computable relation, okay? And you're trying to ask, then you search over all possible natural numbers and you say, is there some element in the natural numbers which sits inside of this computable relation? And if the answer is yes, then that's the computation halting, and otherwise it never halts. And there's no way to know that a priori, whether it's going to halt or not.
Excuse me.
Yes?
Computable functions go from n to n, right?
Yes.
And the halting set is a subset of...
Right, so this is the halting set. It's encoded in the natural numbers. So I'm eliding this fact that if you have a function that's computable f, then it has some sort of index e. So the you can think of this as you list all the possible programs that so every computable function is just given to you by some program which is needed to execute it. Okay, and those programs all have names. So the names are listed by the natural numbers, and so there's some index. Okay, and then you have n, which is the input. Okay, and then so this combination, it may or may not converge, right? So this is a computation that you're asking. You're saying run the eth program on the nth input, okay? And so this pair can be coded as a single natural number, okay? And then this lies in the halting set precisely if the computation converges. So that's sort of an identification that I'm making here. Okay, great. Right, so that's the halting set, and then you can say, okay, well, are you done once you know the halting set? And so it's just some subset of the natural numbers. It's fixed once and for all. If you have access to the halting set, can you compute all functions? Well, no, you can't, because then you can sort of play the same game, and you get the halting set associated to the halting set. That's the written 0 double prime. This is the second Turing jump. And then you can play this again. You can take the third Turing jump and the fourth Turing jump, and you can do this countably many times. And if you've ever wondered how complicated all possible sets that are definable in arithmetic are, it's actually the union of all these possible Turing jumps as up to sort of the first countable ordinal. Anyway, so let's return to the how complicated this set is in terms of determining when two finite simplicial complexes are homeomorphic triangulable manifolds. So, yes?
Can you say again how did you define the second Turing jump?
Right, so, okay, so, right, so you look at all possible Turing machines, which are not only, they're allowed to ask an extra question more than, so these are just computable functions, okay? And these are, you can consider computable functions which have access to this set as an oracle. So they can say, is the number n in the halting set or not? Which is not a computable thing a priori. Okay, and so if you look at the halting set of that corresponding universal Turing machine, you get this thing. Okay, and then you just sort of iterate this procedure and get all the higher Turing jumps. Okay, great. So, so let's look at let's maybe filter this by some low dimensions first. Okay, so in dimension 1, there's almost nothing to say, so I'll just start with dimension 2. Okay, so it's definitely a computable thing to take a finite simplicial complex and determine if it's a two-dimensional manifold. Okay, so you essentially only have to check one thing, which is that if you take a vertex, okay, and you look at its link, the link had better be a circle. Okay. And then you have I'm assuming that these are finite simplicial complexes. I had said at the very beginning that I want all my manifolds to be closed and connected. Okay, so closedness and connectedness are also things that you can check by an exhaustive search. Okay, and then if I give you two finite simplicial 2 complexes, which you've now verified are both two-dimensional manifolds, so then you just see, are they orientable, and you compute the Euler characteristic, and you're done. Okay, so that's nice and computable. So maybe I'll write this the homeomorphism problem in 2 dimensions is Turing reducible to 0. So it's a computable relation. Okay. So what about in dimension 3? So in dimension 3, right, so the recognizing when a simplicial 3 complex is homeomorphic to a closed manifold is still something which is computable, right, because essentially all you have to verify is that the maybe I won't say this too quickly, right? So you have to you look at the link of every vertex, and it better be a 2-dimensional sphere. Okay. So a priori, the link can be an arbitrary 2 complex. Okay, and so then you have to verify that this 2 complex is actually simply connected in order to be able to conclude that it's a sphere and itself also a manifold. But then you can check whether the link is actually a 2-dimensional manifold by everything that we did in dimension 2, and then simple connectedness is just an Euler characteristic calculation. Right? So telling whether or not a 3-dimensional simplicial complex is a 3-manifold is a computable thing. Okay, but now let's consider the homeomorphism problem. Okay, so I take 2 such things. They may be homeomorphic, but the simplicial decompositions that are given to you may be very different from each other. Okay. So what is true in dimension 3 is something called the Hauptvermutung. Which means that for these 3-dimensional simplicial complexes, if they are actually homeomorphic to each other, then they admit simplicial subdivisions which are combinatorially equivalent. So that is to say that you actually have a map between them, which is a homeomorphism, and it takes simplices to simplices exactly on the nose. Okay. So that's something which is true in dimension 3, and it was shown by Milner to be false in higher dimension, I think in dimension 5 and higher. And it's also false for even simplicial complexes that are manifolds. The Hauptvermutung may be false. But what does the Hauptvermutung have to do with sort of computability? Well, computing a simplicial subdivision from a given simplicial structure is a computable operation. Okay? And determining if two simplicial complexes are simplically equivalent to each other is also a computable operation. And the only question is, will this search for a compatible refinement ever terminate? Okay. So that tells you that the halting set, if you know whether some computable relation or some computable search will eventually terminate, then you can determine if the Hauptvermutung will eventually find you a homeomorphism between two three-dimensional manifolds or not. And so what this tells you a priori is that Homeo 3 is bounded above by the halting set in terms of its complexity. Okay. So this has been improved. So it is actually known that it's computable to determine whether or not two simplically presented three manifolds are homeomorphic to each other. But this uses a lot of machinery, including geometrization. So this is not elementary at all. Okay.
What about the Hegardt splittings? Can you use it to?
Yeah, so I think Hegardt splittings, there's this sort of issue of determining sort of the stability, right, up to stability. So I think that is that will give you the same bound here, right? It won't improve you to computable. That's sort of the problem with Hegardt splittings. Okay. So
Isn't that what Hawking was doing back in the 60s?
yeah, right. So I mean, geometrization in some sense builds on Hawking too. So if one wants to give credit to everyone involved, then one should say like, well, Hawking and Thurston and Perelman and Matveev and Rubinstein and Kupperberg. It's a very large joint effort that figured this out. Yes. Great. Okay, so let's keep going up in dimension. Okay, so you may have heard already that, well, in general, you cannot determine if two triangulable manifolds are homeomorphic to each other computably. And what does that mean? Well, precisely what one can write is that the halting set is a lower bound on the complexity of Homeo 4, of four-dimensional manifolds. And this is a result due to Markov. So what's going on here? Well, if you have any finitely presented group, right, so then it has some collection of generators and relations. Right? So what you can do is you can take a connect sum of a bunch of S1 cross S3s. Okay? And what you end up getting is a four manifold whose fundamental group is free of whatever rank you need. So then you choose representatives of the relations. Okay? Those are just loops that are embedded inside of this four manifold, and you cut out tubular neighborhoods of them, and those tubular neighborhoods are going to be homeomorphic to S1 cross the 3 ball. Okay? And the boundary of S1 cross the 3 ball is S1 cross the 2 sphere. Right? But S1 cross the 2 sphere bounds a four manifold in two different ways. It's also the boundary of the 2 ball cross the 2 sphere. And so you glue in the other manifold, the 2 ball cross the 2 sphere, which is simply connected. And so you impose those relations. And so you can realize any finitely presented group as the fundamental group of some compact four manifold. And you can do this all sort of within the class of simplicially presented four manifolds if you're careful about it. Okay. And so what this means is that determining, so if you had some algorithm which took two four manifolds and decided if they are homeomorphic to each other, then it would have solved the isomorphism problem for finitely presented groups already. Right? And that is known to be Turing equivalent to the halting set. It is exactly of that same level of complexity. Okay. So then you cannot get computability in dimensions 4 and higher. Is there some upper bound here? Okay, so is there some sort of, so it's a priori, it's possible that this set is of arbitrary complexity. It may not even be given to you by an arithmetic sentence at all. An arithmetic formula may not cut out the homeomorphism relation. However, there are some tools, classical topology from the 1970s, which come to our aid. And so what it turns out is true is that if we look at, so in arbitrary dimension, we have the this homeo of manifold relation inside of n cross n is bounded above in complexity by the second Turing jump. Okay, so what this means in terms of how complicated this is as a subset of the natural numbers across the natural numbers is precisely as follows. So basically what this means is that so there exists a quantifier-free predicate maybe R of x, A, and B, such that x is in. So this is an arithmetic predicate. So this is so x and A and B are tuples of natural numbers, and this is just sort of adding and multiplying them and comparing them in terms of relative size, so that x is in homeo manif if and only if for all A there exists a B R of XAB. So it's very, very controlled in terms of its quantifier complexity. Okay. Perfect. So in the remaining time, let me maybe indicate a little bit of why this is true. Yes?
As my previous comment, so in dimension 4 now there are the trisections.
Uh-huh.
Can one use this to go down to prime?
I think that only works for smooth four manifolds.
Or PL?
Yeah. So this is supposed to be true for all triangulable manifolds. So I'm not sure. Yeah. But it's plausible. In any case, if it's not, then you only have to sort of go one Turing jump higher. So it's maybe not too bad. Okay, so implicit in this statement are really two things, right? So first is that you're recognizing the actual manifolds as simplicial, among all simplicial complexes. So there's the manifold recognition problem, and then there's the homeomorphism problem. So and then the homeomorphism problem. Okay, so for the manifold recognition problem, this is something that I mentioned already in the case of two-dimensional and three-dimensional simplicial complexes. So you have to look at links of vertices and then more generally at links of cells in a simplicial complex, and they have to be spheres of the correct dimension. Okay, so that's something which is true in low dimensions, although in dimensions 5 and higher, certainly, this is not true anymore. But something almost as good is true. So there's a result due to Cannon and also Edwards, which says that if you have a simplicial complex, okay, and you want to know, is it homeomorphic to a manifold? Well, so in dimensions 3 and higher, this works. So you have to look at vertices, okay, and you look at the links of these vertices. And so they need not be spheres anymore, but they have to be simply connected homology spheres. So this is so a simplicial complex in dimension at least 3 is a manifold if if the links of vertices are simply connected homology spheres. Okay, so enumerating the links of vertices in a simplicial complex is something that's sort of easily computable, okay? So then you have to do two things. You have to verify that that link is actually a homology sphere, which is something that you can do very mechanically. I mean, we know, so from any finite simplicial complex, you can compute the homology by this completely mechanical procedure of simplicial homology, okay? And you just check that it has homology in the right dimensions of the right dimensions. And then for simple connectedness, that's slightly more complicated, right? So the simple connectedness is a statement about the fundamental group, okay? So, and again, a priori, these are not, the links are not themselves assumed to be manifolds. They just sort of behave like spheres from the point of view of algebraic topology, but you can still write down a presentation for the fundamental group from the simplicial decomposition, okay? And then, right, you have some finitely presented group, and it had better be the trivial group, okay? And so, in particular, this is reducible to the halting set, okay? So to determine whether a particular presentation is the trivial group or not, okay? So, right, so in this part of the theorem, right, so the two parts are recognizing when you have a manifold among simplicial complexes. So that part is just bounded above by the halting set, so that's fine. And then the homeomorphism problem. Right, so what comes to one's aid is something called the alpha approximation theorem. So maybe I'll write this for the homeomorphism problem. So this is something called the alpha approximation theorem. So in dimensions at least 5, this is due to Chapman and Ferry. And in dimension 4, this is due to Ferry and Weinberger. And so basically the question that the alpha approximation theorem is trying to answer is, well, let's say you have a homotopy equivalence between two spaces, okay? How close is it to a homeomorphism? Or can one just sort of conclude that if you have two manifolds, right, and you're given a homotopy equivalence between them, is that homotopy equivalence close, maybe in the C0 topology, to a homeomorphism between these two manifolds? And the alpha approximation theorem tells you that yes, under certain conditions, right? So you have manifolds M and N. And so I'm just going to assume that these are both closed, right? So they have no boundary, because otherwise there's some sort of complication that occurs on the boundary, right? And so, right, so you have maps F and G between them, right? So that, right, so F composed with G and G composed with F are both homotopic to the identity on, so, right, this should be on N, and this should be on M, okay. So the alpha in alpha approximation comes from choosing an arbitrary open cover of N and naming it alpha, right? So if you have, so alpha is an open cover of N, alpha an open cover of N, then we say that the pair FG is an alpha equivalence if this homotopy F composed with G to the identity is given, sorry, so let's write it down as an actual function, is given by a homotopy, let's call it eta sub t, such that for all x in N, right, there exists a U in alpha such that eta t of x is contained in U for all t, right? So what this is, so that's one condition, right? So this is saying that, right, you have this homotopy which a priori could be really wild. It could move all over the manifold, but this is saying this is a small homotopy, small in the sense that it's controlled by alpha, so that the track of this homotopy from F composed with G to the identity is contained inside of some fixed element in the cover. And also you have like, so G is also homotopic to the identity by some theta sub t, such that, right, for all y in M, there exists a U in alpha, such that if you write F of theta t of x, this lies in U for all its life. Okay, so what the alpha approximation theorem tells you is that in dimensions 4 and higher, if you have two closed manifolds that are equipped with an alpha equivalence for arbitrary alpha. So alpha is allowed to be sort of any open cover. Okay. Then this map F, or G if you wish, is homotopic to a homeomorphism between M and N. Okay. So it's an incredibly powerful conclusion, right? So if you have these controlled homotopy equivalences on arbitrarily small scales, then in sufficiently high dimension, these underlying manifolds were actually homeomorphic. Yes?
Is this a controlled Borel theorem?
Controlled Borel theorem. I guess so, yeah.
That their homotopy implies homeomorphism?
Right, if you have controlled homotopy equivalences on arbitrarily small scales, then it's a homeomorphism, yes. Okay, so then maybe just to wrap up everything that I'm saying here. Okay, so then how does this feed into the theorem that we have here? Well, so if you look at just arbitrary simplicial complexes, which you now know are actually manifolds, then you can code rational maps between them. That is to say, maps that are defined on the vertices, say from M to N, right, and which extend to the interior of every simplex by an affine map. Okay. So those can be coded as just simply natural numbers. And similarly, you can code rational homotopies of rational maps. Okay. And so then you don't really have to do that much more. I mean, so you express a computable relation that says that, essentially, that there exists a rational controlled homotopy between homotopy equivalence between M and N. Okay. And so saying that an arbitrary homeomorphism or an arbitrary homotopy equivalence can be approximated by such a thing is a classical result due to, I think, Zeeman. And then sort of why the zero double prime comes up. I mean, you can see that there's sort of this existence quantifier that says, well, there exists some homotopy equivalence that's controlled, and then where does the for all quantifier come in? That makes it zero double prime. Well, at all scales. So if at all scales there exists this control homotopy equivalence between these finite simplicial complexes, then they are actually homeomorphic to each other. And then the converse is simply given by approximating an arbitrary homeomorphism by a piecewise linear defined map on simplicial complexes. So I think maybe this is a good place for me to stop with a few minutes for questions. Yes?
So there's no way an AI machine will ever do this.
I don't think so, no.
This is way beyond the capability of user set.
Yeah. I mean, what AI might be able to do is to maybe try and prove this. That would be pretty cool if you could get a lower bound. That would be, so I've talked to a few people working in logic, and they say that there's no really known finitary problem whose complexity is known to be beyond the first Turing jump, so that the second Turing jump is a strict lower bound. So that would be cool. I don't know how to prove that. So what you'd have to do is, right? So I mentioned in this sort of very quick introduction to computability theory that I did here about, Turing numbers have, computable functions have indices, right? And so you have an index E, which is just the name of a program that you're executing, right? And then you have an input N. Okay. And so you can look at the possible values that the ETH program spits out over all its possible inputs, okay? And that, what you end up getting there is what's called a computably enumerable set, okay? And a computably enumerable set, it could be very complicated. It could also be very simple. It could be just empty. Like you could build a program that just loops on every possible input. It doesn't ever converge, so it doesn't enumerate anything. So then consider the indices, which have infinite ranges. That is to say, right, if you look at the ETH program, okay, and this is viewed as a function from the natural numbers to the natural numbers, okay, it has some sort of range. When is this range infinite? Okay, so sometimes it'll be infinite, sometimes it won't be. Can you characterize the set of indices, names of programs which will have infinite ranges? That is exactly the same complexity as 0 double prime, right? Because this is, you can, again, with that sort of, for all, there exists computable complexity thing. You can say like, okay, so for all n, there exists some stage in the computation where you've enumerated at least n elements, right? So that's how you can see that these are really the same thing, okay? So then what you'd have to do is you'd have to find some way of encoding in some computable way, computably enumerable sets into finite simplicial complexes so that two manifolds are going to be homeomorphic to each other if and only if, if and only if you can, if and only if maybe like the joint computably enumerable set that you encoded there is infinite or something like that. It's going to be something very, very difficult to actually realize with finite simplicial complexes. So in any case, if this is true, it would be very surprising and probably very difficult to prove. It may be false. So I'm not even going to claim that as a conjecture.
Are there natural geometric questions where you get like even higher Turing jumps as upper bounds? Or is this what you just get for manifold?
I don't know the answer. Yeah.
Any related question, but not related to computability. Does PL homeomorphism know about PL structures as a group?
That's a good question. I don't know. I think it probably should. Right, so that again circles back to this question that Yash asked, or that you asked during Yash's question, right, about whether or not there's a Higman's theorem for maybe PL homeomorphisms or for smooth maps, right? So it is true that if you look at the diffeomorphism group of a manifold, then it knows the smooth structure just from the group theory and just from the first order theory. But for PL manifolds, I don't know. I would suspect that the answer is yes, but I don't know how to prove that. Right, and the conclusion of this alpha approximation theorem, it does not give you anything stronger than homeomorphism. So even if f and g are always smooth at all scales, it doesn't conclude that m and n are diffeomorphic to each other. It only claims that they're homeomorphic to each other.
Any more questions? Almost again.
Yeah.